just remembered something. We'll get back there. Okay, so X is the cross product, and I'll show you in just kind of cartoon form what it means, and it's the best way to think about it. So you guys have probably already seen. I don't know why this thing's acting up. No, it's tough to do it this way. So I know you've seen the X, Y, and Z axes before. So we'll just let the X-axis come towards us. We'll let the Y-axis kind of head off to the right here. And we'll let the Z-axis go up. So here's how the cross product works. If I do X, sorry, they look a lot alike. I'm trying to make that X kind of cursive. X cross Y equals Z. So like and you can see that obviously on the page, but let me explain it in a little bit of more detail. So, and this is critical now to how the electromagnetic field works in a motor, in a generator. So, if I have my my hand, this might end up coming up backwards, but this is my right hand, and I've got my right hand pointed to the left, and I'm going to take it and cross it into my palm. So you can think of my fingers as being the X-axis, my palm as being the Y-axis, and I'm actually spinning that X-axis into the Y-axis, and there goes the Z. So you can think of it just like your hand. So if I take the, again, take the X-axis and sort of spin it towards the Y-axis, the Z pops out. Now, the same thing happens if I take the Y-axis and spin it towards the Z-axis. Oops. The Z-axis. The X-axis pops out. And if I take the Z-axis, cross it towards the X-axis, the Y-axis pops out. So it doesn't really matter that I was holding my hand, this way, and there goes the Z. If I hold this way, there goes the X, or hold the other way, and there goes the Y. And there's really nothing special about the three directions. I mean, we always kind of think of Z as up because it's working against gravity, and then you might have your longitude and latitude. But that's the cross product. And that part right there is fundamental. Let's just go page up. It's fundamental to understanding this diagram, because the electric field is always perpendicular to the magnetic field. Then finally, this is where it's a little kind of fun, interesting, weird, but the now I think we could all agree that right where you've got most of your electrons flowing, you got high voltage. Further away, you got low voltage. And this gradient upper, this pen's not working out right. Upper, put the R in there. Operator is the change in the voltage gradient. So, and that's going to be a little tough to explain, but let me try. Let me see if I can explain that guy. I'm going to try to keep the the gradient operator there on the bottom of the page, and I'm going to try to keep the picture up here on the top. So again, this E is how quickly voltage is changing. So if we sort of take, and I'm going to try a new pen color, I think we can see that if we sort of move any way away from the high voltage, I'm just going to kind of head out in some random direction away from the high voltage. That's kind of the direction that E is pointing, sort of out. And as I move further away, you kind of get a less and less voltage, if that's making sense. As that changes, this, let me think about this one second. That del operator is telling you how quickly it's changing. So you can almost think about that the red arrows I drew as a car coming to a stop. So at the beginning of your trip, you had really high velocity. You take your foot off the brake, and now lower and lower and lower. You kind of got less and less energy, less and less voltage. Well, those arrows are changing, and that's what that delta is. It's saying that as I move further away, it's changing. So as this thing becomes less, the changes in the magnetic field also change less. And that's why, I don't know, I guess that's why if you are, if we're over here like turning the motor on and off, you're gonna see that voltage is gonna change, and all of those voltage changes are gonna create magnetic waves, right? So that's why you turn your microwave on and your radio goes crazy, or etc. So does that at least help a little bit with the relationship between electricity and magnetism?
Yeah, I've got a good.
Yeah, it's a little confusing, but that's exactly what those symbols mean. I mean, I think pretty easy to understand what obviously all time there's change, magnetic field. And again, that E is not the voltage; it's the voltage gradient, because as we know, it changes through space. The cross product I showed you is that kind of funny way of multiplying, and what it does is it makes sure that everything always stays perpendicular. That cylinder is perpendicular to the torus, and then the gradient operator is just, again, just showing you something that's perpendicular. Okay, so what else do we need to discuss here? That's kind of the main, the main thing I want to show, so we at least
For
have
last
some.
week, yeah.
Yeah.
I mean, the only question I had on, it's question 3 anyways of last week.
Okay.
So it says household current and voltage available at a standard wall outlet at 120 VAC. What is the value of all the following?
Mm-hmm.
And then it has all the stuff but instantaneous voltage, you would have to have another time component, wouldn't you? Because I didn't see anything in the book of how to get instantaneous voltage out of just what the value's given.
Oh, okay.
So all I did was kind of put in the definition of instantaneous voltage. Instantaneous voltage.
Okay.
It didn't make any sense to me because all the other ones you can do, frequency, root mean square, average, peak, and peak to peak all make sense using that, but instantaneous needs another time value, does it not?
Oh, tell me what number it is.
You're on the wrong. This is last week's. You're on this week's.
2B. Oh, you need to be on assignment 2.
I don't know if you wanted us to see the whole course, but I can see the whole course.
Oh, that's okay.
Okay.
I know sometimes you guys like to work ahead. I don't have a problem with
We do?
it. Some of you might, some more than others.
So.
Oh, number 3, household current voltage available at a standard wall outlet is 120 VAC. What is its value in the following? Okay, so frequency, I'm guessing you came up with 60 hertz on that.
Yeah.
RMS, did you calculate that?
Well,
Did you get the formula for it and everything?
Yeah, RMS turns out to be 120. Right? Did you get 120?
For RMS, it's not going to be 120. Let's do that
Well,
one.
already. You're a week behind.
Okay.
So-
Is that the one where you multiply it by .707?
Yeah, that sounds about right.
I don't remember what I did on the record.
Yeah, let's,
Dollar short comes to mind. Your graph.
let's look at,
Because then I'm pretty sure that makes all my other ones wrong.
oh, okay. Well, you know, I think it's worth covering now.
Did you get 170 for peak voltage?
I think so, yes.
Okay. So I mean, I got 2 of them. 108 for average voltage. That's what I might have flew by.
Oh, 41.
Because it sits there and talks about, yeah, so page like 42.
Yeah.
41, 42.
40.
Okay, yeah. So that, yeah, let's take a look at that. So here's how to think about RMS value. So here's a wave, sine wave. We'll just go with the sine wave. We'll go with a full value, and there's your 120, right? Is your amplitude. And so, R, M, S. First of all, what are the R and the M and the S stand for?
Root mean square.
Okay, so they're written in that order, but you actually do them backwards. So if I take this this value of 120 and square it, so 120 times 120 equals 14,400. That's going to be the max value up here, right? 14,400. That's going to be way the heck up here, right? Same thing here, negative 120 squared, so negative 120 squared is also going to be some gigantic wave way up here. So what I'm going to get are 2 separate, actually I'll make that a different color. And I'm basically, when I do a square like this, it's more or less a rectification, right? Because any positive number squared, any positive number squared is a positive number. Any negative number squared is a negative number. So now I've done the square part. Now what I'm going to do is take the mean, and the mean is more or less just the average of all of those values. So you got some high stuff up here, you got some low stuff up here. Somewhere is just the mean. There's the green line. The next thing is the root, and I don't know exactly what that green line is, but when we take the root of it, it's going to come back down. It's going to be a smaller number. I think I actually have a Excel I can post for a solution. As it turns out, I think what you just said there, Jesse, is correct. As it turns out, the RMS value of voltage or current is about 70%, or 0.707 to be exact, of the peak value. So if we just take 120 times 0.707 equals, it seems a little low, 84.4. I think that's what it is, though. Yeah. Peak value, 0.707. And then the next one is average AC value, means the instantaneous values averaged over half. So again, this red line here is squaring all of the instantaneous values. So that's more or less what what is the value of the following? Instantaneous voltage. The way, I guess the way I would write that, the instantaneous voltage, you know, if we wrote, if we just wrote the voltage, so this is the formula for the voltage. The voltage equals 120. That's the number of volts times sine
So is 120 in this the peak value then?
yes.
Okay, that's why, okay, oh, that's wrong.
Okay. Is that working?
Well, I turned it in, but you know, whatever.
Okay. So yeah, so 120 is the peak voltage, and that's why some people are like, oh, what's the wall voltage? Well, normally coming in your house, it's never exactly 120 either. I mean, there's no way to make any voltage exact, but the idea is, as long as the voltage coming to your house is like no greater than 123, no less than 117, probably all your appliances are going to work correctly. Then I think you can just get the rest from that little table on page 42 for the average.
Well, I have way more questions about 214 than I do
Okay.
213.
All right. Let's just wrap up. Let's just wrap up 213 now. Stop the recording.